Alright, class, I want to tell you that. Are there any questions about anything that we've covered in the homework? Did you all, I don't know if you had a chance to look at it, I put up all the information about the Fourier series analysis that I've been doing in class. Did you all get a look at that? Alright, so what I'm going to do today, I'm going to start basically where I left off Friday, and I'm going to develop the final form of this, the envelope form. Tonight we're going to get some problems, a bunch of calls related to this. And let's see. I understand there might be some severe weather tomorrow. Anybody see that? They have, I mean, that's what I heard in an announcement. I don't know if it's going to hit here or not. If I'm wrong, I hope I'm wrong.
It'd be nice if I have radar or no radar.
Okay. Anyway, when we looked at this, we found out that in general, this waveform here, basically, I'm just going to cut to the chase on this one. It's repetitive. The period T, on time tau, rise time, tau rise, fall time, tau fall. This waveform with amplitude A, and this is a V of T, ends up being equal to, V of T is equal to the summation of C of n e to the j n omega naught T from n equals minus infinity to infinity. Here the value of C of n, remember we got this through the derivative method, everybody? We took two derivatives, and then we found the Fourier series of that impulse series, and then we backed it out with 1 over j n omega naught twice. And we got C of n, a form that I left you with, had it's basically A times the sinc of omega tau rise, or sorry, I went and I did pi. I left you with a. If you look in the notes, the last thing you saw, I think I got it down to where I had this is pi times n f naught, and it was times the sinc of pi n f naught times tau. And this is times f naught times tau rise, and this was over P. And I believe that's what I left you. These are sinc functions. Is that right? Yeah. So then there's also the phase. The phase we won't really care about. But there's e to the minus j n, and it's f naught, and it's tau rise plus tau. That's a phase. I'm just going to pick it up from there. So we figured that out. That's the value of C of n. Now, what's important about this is that this function right here is only at discrete values. Do y'all follow me? Did you have a question back there? Did you have a question? It's only at values of n. So if you look at this and take a magnitude, you just took a magnitude of this versus f, what you'd find out is you're going to get this kind of a deal. And then when the sinc waveform starts hitting it, it'll start tapering down, tapering down. Do y'all follow me on that? I'm just trying to give you an idea of what that looks like. What normally you do at EMC, you worry about worst case phenomena. So we really don't care about how the sinc waveform, these waveforms are going to basically vary as a sine waveform. They go up, down to zero, up, down to zero. What we care about is the envelope that actually these things ride on. Now I'm gonna take it from there, and please watch this part, this is important. So, now I'm gonna go back to this Fourier series here, and I need this part of the board. Now if you look online, there's a note set on this. I put up a PDF note set that really discusses this in great detail. Did anybody, how many looked at that? Just tell me the truth. 1, 2, 3, 4, 5, about 5 or 6 people. Please do it, because it does a great job explaining all this. So now what I'm gonna do is this. And all this, and I'm gonna show you the final form. This is the form you need to understand and know. So here, we saw that V of t was equal to the summation from n equals minus infinity to infinity of C of n e to the j n omega naught t, right? I'm going to break this up in 2 series. This is going to be a series from n equals minus infinity to minus 1, C of n e to the j n omega naught t, plus C0, plus, and this is going to be a summation from n equals 1 to infinity of C of n e to the j n omega naught t. Now I did it for a reason. Remember, when we have C of n right here, this has a magnitude and a phase. Angle is C of n. Everybody with me on that? It's, in general, a complex number. If you think about this, C of minus n will have the same magnitude, and the only difference, because of the fundamental definition of C of n that I'll put here, remember C of n is 1 over t, the integral from minus t over 2 to t over 2 of the function v of t times e to the j n omega naught t dt. Now, I want to just tell you something. Take a look at that. What is C? This is C of n. C of minus n is just going to be the same thing, still v of t, but now it would be e to the minus j n omega naught t dt. Y'all follow? Only that phase term changes, the negative signs on the j. Y'all follow me if it's negative n? So that means down here, C of minus n is that, the only thing that happens is the angle becomes negative. That's the only thing. All right? Just try to appreciate that. Same magnitude, only the angle. If it was a plus 45, it becomes a minus 45. That's it. Only thing that changes. Now, why did I say that? Because here, if you look at this, I can say that this part now, I can say it's the summation from n equals infinity, or really from 1 to infinity, and I can put C of minus n here. And actually, let me group this one next. Now look, if it's going from n, remember this is going to be a minus right there too, right? Y'all with me on that? Anywhere there's an n, I'm going to put a minus n. This was from minus 1 to, or from minus infinity to minus 1, where n is counting negative. If we let n count positive from 1 to infinity, we put the negative sign there. Y'all follow me? It's the same thing. Just take a good look and convince yourself. I mean, do y'all see that right there, class? If you go from n equals minus infinity to minus 1, if I go from plus 1 or from infinity to plus 1, I can put a C of minus n there and a minus there. Y'all follow me? It's the same exact mathematical state. Now I take that, and because I'm counting positive from 1 to infinity, this is from 1 to infinity, so I can add that right here. And say that's C of n e to the j n omega naught t plus C0 out here. Y'all with me? Again, a lot of this is going to come together in a second. So I do that. Anybody got an idea why I did this? Now I'm going to put in the actual magnitude and phase value. So here, what we get, if I do it, well, I'll do it right now. Now I can see what I get. And I'll take n equals 1 to infinity. I'll take that one first. So it's going to be C of n, and I'm going to put the magnitude for times e to the j n omega naught t plus the phase angle of C of n, and it's plus magnitude form of C of n, that's this, the negative one, and it's going to be times e to the minus j n omega naught P, but it's also gonna be plus the phase angle of C of M. Now, that is actually the minus phase angle that's associated with this. Do y'all follow me? How many see what I'm doing here? You with me on that? You have a question? Anybody back there? All right, you okay with it? If you follow me, why did I do this? Want to take a guess, anyone? Think about what I always try to drift to. Trig functions, right? I always am looking for a way to condense it down. What is this trig function right here? There's a plus C0. What's e to the j theta plus e to the minus j theta over 2j? Cosine, isn't it? Isn't it? Sure. Now I can say, and I'll do it over here, I can say that the reason I did this, and this is the important part, now I can say that this itself is equal to the summation of really 2 times magnitude of C of n times the cosine of this. Cosine of n omega naught t plus angle of C of n plus C0 out here. And this is from n equals 1 to infinity. Y'all with me on that? Now, let me ask you this. Why might that be of interest? Anyone take a shot at that? Why would I want a cosine series? All right. You think about it, just form that question in your head. Now let's put it over here. Because what do we know when we do any kind of a circuits problem with a sinusoidal or cosinusoidal excitation? How do we go about doing it? That's right. So here's what I'm saying. This form will have all the frequency components at n omega naught, all right? There'll be first harmonic is n equals 1, second harmonic n equal 2, third harmonic n equal 3, and so forth. Each one of those can be analyzed separately, its effect on a circuit, and the results summed at the end. So here's why I'm saying that. Think about this. If I have plus or minus a voltage source, and I'll just put V of t is equal to some V naught cosine of omega t plus some theta. And I have some circuit, I'll just put a resistor here, R, and an inductor here, L. And I want this current. I want I of t. I want time delay. So how, as engineers, would you solve that? If you're going for a job interview at Google or some high-paying job, they're going to ask you things like this. They want to see how you think. So how would you do it? You know, as engineers, this is cosinusoidal, continuous excitation, right? We wouldn't do it that way. We would put a voltage V naught at the phase angle theta, wouldn't we? Then what else would we do? Think about it. Now, the R is an R, right? But what happens here? J omega L, right? So I put J omega L. Now I don't worry about I. Now I get phasor I, right? So how do I get phasor I? Just tell me. Own words. I take the voltage divided by the impedance. Y'all with me? I'll get that. So now I'm going to get phasor I, is this voltage, V naught angle of theta divided by R plus J omega L. Y'all agree with that? Doesn't matter what omega is, doesn't matter what L is. Once I get that, how do I get the time domain form? Well, remember, this is really what? It's some magnitude of I, right? At some angle of theta I. Isn't it, class? With me? Now, how do I get I of t? Remember this. It's the real part of the phase times e to the j omega t. That's all it is. All right. Now, when you take a look at that, what does that automatically mean? This is equal to the real part of that, which is magnitude of I, right? Then I'm going to have e to the j, and this is going to be omega t plus the phase angle. Is it not? You can combine it like the exponentials. Please watch this. This is important. When people go out to interview, especially, and they fumble around with something like this, not a good sign. You should know this is like you do V equals I and that stuff. All right. Now, if you look at the definition e to the j theta, that's simply cosine of theta plus j sine of theta, isn't it? What law is that, or what identity? Euler's, E-U, right, L-E-R-S. Don't remember this, you're gonna use it all the time. How many have taken comm in here? Couple people. In comm, you're using this kind of identities all the time. Communications, you're gonna use it in your higher level courses all the time. Get familiar with it. So this, when I look at this, the magnitude is just I, right? But then when I expand that, I get a cosine plus j sine, right? Can you all see this? The real part of that is just the cosine. It's just this, and then it's gonna be times, well, I'll put it on this side. It's just gonna be magnitude of I, cosine of omega t, plus the phase angle associated with the current. And that's it. Now you're back in the time domain. You all agree with that? That does not account for the transient portion of it. If they had a switch that turned it on, it wouldn't. But we're assuming steady state operations. Now, why did I do that over here? Or why am I interested in this? You see how each one of these is a phasor? Can you all see that, class? Magnitude and phase. It's at each different harmonic. You would have to evaluate the circuit impedances at n omega, not omega. Then you would find, if you had a system, and this is really the last part on this part of it, and I'll show you how to do the analysis of frequency. By the way, you know, when I remember teaching long ago, circuits, I didn't do a lot of going from time to frequency and then from frequency to time. It was usually, I think all of Irwin's books and stuff, he just puts tangent and angle at 30-degree sources, and he would give you like J40 ohms or something like that for an inductor. And you never went back and forth, so you weren't used to that, but you should be used to this. Make sure, because this is going to happen a lot. So back to that thing. Now, if I have any kind of a source, voltage, or current, doesn't matter, and I have a system with a transfer function h of omega. Now, we can get that if we have a circuit and we do the analysis in the frequency domain. We have input versus output in the frequency domain. You all with me on that, class? Now, you have an output. Something here. And you want this. Well, this V of t, if it's a periodic waveform that's feeding it, V of t can be represented, and by the way, this representation doesn't matter if it's trapezoidal or anything. If you have a periodic waveform, you can get C of n for the exponential series, and you can get this. And that means this waveform, or the output of this, when I look at it, V of t here, the input, will be equal to some summation of C of n e to the j n omega naught t, n equals minus infinity to infinity plus C0. That can further be represented as this series. Do y'all follow me? Because that's a cosine series that's the same exact information as that one. Now, if this is used to show the input waveform, I'm going to assume that is, so I'll put it down here. Plus C0. Then my output here will be equal to, and here's what happens. I go ahead, and I'm not going to do the whole 9 yards here. I could turn this into a phasor where each one of these things will have 2 C naught, or C of n, as the magnitude, and it will be at an angle C of n. Y'all follow me? I feed that into the circuit, and I get the output for each one of those. Y'all follow me? Then I go back to the time domain. When all is said and done, I find this to be the case. This is equal to C0 times H0. That's the transfer function identified at 0, at frequency of 0. Plus, then it's equal to the summation from n equals 1 to infinity of 2 times magnitude of C of n times the magnitude of the transfer function at n omega naught. Remember, you're going to do this for each harmonic. Tell you what, let me go over here and do it on this part. I'm gonna say my V naught of T will be equal to this. It's gonna be equal to C0 times magnitude of H. C0 is just the average value of the function over one period. You all follow me on that? So if it's a sinusoidal waveform, it's 0, but it doesn't have, then it's gonna be plus, and now you're gonna have a summation from n equals 1 to infinity of 2 times magnitude of C of n, magnitude of H of n omega naught. Then it's gonna be times the cosine of n omega naught t plus the phase angle of C of n plus the phase angle associated with H of n omega naught. Follow me on that, class? That is the output. And signals and systems, when I've taught, does anybody have me for signals and systems in here? When I teach signals and systems, I do this problem to show you how signals and systems is used in circuit analysis. How many of you heard of SPICE, or LT SPICE, whatever? SPICE uses this type of analysis in the frequency. Right? That's all they're doing. And here, you get a time domain value, but you're analyzing the filter's output, or the filter's response at each harmonic. Do y'all follow me? Now, I'll give you something on this one to work on. But I can just tell you, there's probably a few questions, so let me do a quick example, and then I'll get to the actual, by the time of this frequency waveforms. So, now, the next thing I want to show you is, if that's the case, let's do an example. Suppose I have this. I'm going to give you a waveform. I'm trying to think of it. All right, I'll give you this waveform. Here, I'm just going to make it easy. T equals 1 second. There's no rise time. This is going to be equal to tau is 1/2 second. Magnitude here is going to be 2, and this is going to be a voltage waveform. And the period is 1 second. All right, this is what this clock is, right? Then it's a voltage here. Comes in, and I'm just going to do something. So I'm going to have an inductor L, and I'm going to have a resistor R here. I'll let L equal to 1 Henry, and I'll let R equal to 20 ohms, okay? And now, I want this V out of T. Can y'all follow me on this? Take a good look. All right. I don't think you'll be asked this question, but I could see it happens. All right, so first for V of T, you all agree we need a Fourier series for that, right? So, what method am I going to use? Probably. What I'm going to do is take the derivative of that, right? Without going through the whole spiel again. If I get V prime of T, right? V prime. Now, what do I get? Remember, it's the periodic. From 0 to 2, it gets a delta function here of height 2. And then at 1/2, it gets a delta function negative of -2, right? You all agree with that? Can you all see that? All right. I know that itself, and it'll be periodic, so you keep on going forever. The value of C of n prime, right here, I know my V prime of T is a periodic, it's a periodic signal, so it can be represented as simply a summation, right, from n equals -infinity to infinity, right? And now it's going to be C of n times j n omega naught times e to the j n omega naught t, or as the summation of C of n prime from n equals -infinity to infinity. Let's see that prime a little better. E to the j n omega naught t. So I know it's periodic, and I'm looking for C of n prime. So C of n prime is equal to 1 over the period, integral, and I'm going to go from -t over 2 to t. Actually, let me go from -t over 4 to 3t times 3/4. It's still over a period, but that way I don't I don't start at one of these points and end at another one. I'm gonna move it so I don't have to. And then it's gonna be of that functional form. Well, this functional form is just 2 magnitude, and it's gonna be delta of t minus delta of t minus 1/2, right? That's the functional form of my v prime that would go in here, and it's times e to the minus j n omega naught t dt. You all agree with me there? I'm going through the whole 9 yards on this one to show you, right? Now I've got the series, now I'm going to evaluate this. What is this? How does this evaluate? Now t itself is what? It's 1 second, isn't it? Yeah. So I don't even need it. Right? So when I look at this, what happens? I have 2, the delta function turns on at 0, this one, right? So how do I get the value of the integral? I simply evaluate anything else inside that kernel of integration. And at the time, t equals 0, which is 1. Y'all agree with that? So it's 2, and this is 1. Then I have a minus sign, right? This one turns on at a half, right? When t is a half. You agree with me? That means I evaluate this at a half, so it's going to be e to the minus j n omega naught times 1/2. Now, if you take one look at that, this is really going to be 2 times 1 minus, and this right here will be e to the minus j n, since omega naught is 2 pi f naught. And if you look at this, f naught is just equal to 1 over the period, and that's 1 as well, isn't it, class? Y'all with me? So this becomes e to the minus j 2 pi divided by 2, or simply n pi right here, and that's c of n prime. To get c of n, I divide this by j n omega naught, and I have c of n. So if I divide this by j n omega naught, j n, since f naught is 1, 2 pi, it's just j n times 2 pi downstairs, and that is equal to my c of n. Now, anybody want to take a guess at an easy way to do it from here? Now, this is right. You don't have to go any further, but if you look at this, remember how I'm always pulling out half angle kind of things, e to the j half angle? You can make this what? It would be 2, if I factored out e to the minus j n pi over 2 here, this would become e to the j n pi over 2 minus e to the minus j n pi over 2, right? As such, and still over j times 2n pi here. And what's this? Anybody? You don't have to do it this way. I'm just showing you how I do. Doesn't that start to look like a sine? Isn't that really 2j times the sine of that? Sure it is. So this becomes 2 times e to the minus j n pi over 2. And then it's going to be times 2j times the sine of n pi over 2. And it's over 2j n pi. You can see right away the 2j's cancel. Can you all see that, class? In the back there, you guys can see it? All right. So the 2j's cancel. I come down here. And now, this is the form I have. Anybody else want to see one thing? Does anybody see where I might be going next? Take a guess.
Sync function.
That's right. Divide top and bottom by 2. And now I have it. This is simply e, and I'll put it up here. The actual value of c of n for that waveform is simply going to be equal to e to the minus j n pi over 2 times the sink of n pi over 2. Now that I've got that, I need my transfer function here, right? The transfer function would be v out over vn. So over here, what would it be? Actually, what do we do here? That's right. Now I put this as its impedance to the frequency domain. So it's gonna be J omega naught n, right? Or n, omega naught is just 2 pi, isn't it, class? 2 pi because the actual period is 1. So F naught is 1, and then 2 pi times 1 is just 2 pi. So I have that times 1 is the impedance, and if I want the actual H function, what is it? H of n omega naught, right, or H of n times 2 pi. That's the output impedance, which is 20, or the load, you might say, over 20 plus, and this is going to be J n pi. You all agree with that? How many see this? You okay with it? Don't let it scare you. It's not that big. Now, over here, that's the magnitude and angle, right? That's what I'm trying to do. Get magnitude and angle. Come down here, this has a magnitude of what? 20 over what? Square root of 400, 20 squared, plus n pi squared, correct? Y'all agree with that? I'm squaring this term, taking the square root, correct, class? With me? And how do I get the angle here? Isn't that the inverse tan of n pi over 20? So downstairs it would have an angle of tan to the minus 1 of n pi over 20, right? Opposite over adjacent. Y'all follow me? Now I don't want that angle downstairs. I come upstairs with it. Correct, class? Now, so I'm going to just flip it, and that becomes negative. So this has an angle here of minus tan minus 1, or inverse tan, or arctan, of n pi over 20. Everybody with me? I want to make sure. It's got a minus sign there. Yeah.
What happened to the 2 attached to the pi on the impedance of the inductor?
It magically vanished. That's my bad. Thank you very much. That wasn't intentional. Once in a while you do it intentionally, see the benefit. Y'all with me? Okay, now I have that. Now remember a board or two back there, I went through and I simply took that expansion, the cosine expansion. Oh, I need to find I need C0, by the way. I didn't do that yet. This one you have to do separate. What's C0 for that, really? Isn't it the average value? Y'all agree with that? Take one look at that, can you tell? That's a half second on, 1 second period, height 2. What would it be? The area under here is what? 2 times a half is 1. The period is 1, isn't it? So it's, say it again. Isn't that height 2? 2 times a half is 1, right? Divided by 1, 1 over 1 is 1. No, I'm just saying, I make mistakes. You all with me? All right, now I've got C0. What is H0, by the way? Just looking at it. What's the transfer function when n is 0? Just take one look. What's the impedance up there when n is 0? 0, right? It's 0. All the input voltage is on the output. Correct, class? All right. So now I'm going to do this over here. So now, coming over here, I can say my V out of t for this problem is equal to H0 times C0, or just 1, isn't it? Well, it's 1 times C0 is 1, so it's 1. Plus, and then you have that summation, n equals 1 to infinity of 2 times the magnitude of C of n. The magnitude of C of n is just going to be, oh, did I erase it? That was that sinc function stuff, wasn't it? So, I know it's the magnitude of, what was the coefficient, was it 2? Can you look back and tell? For the sinc function we have for C of n, is it 1?
Yes, 1.
Okay. So this is going to be 2 times, and it's the magnitude of, and this is going to be the sinc, right? N pi, over two, n pi over two, right there, and you don't need the phase, correct, class? Isn't that it? Now the magnitude of the transfer function, which is just what? 20 over the square root of 400 plus n pi times 2 squared. Sorry about that. Right? Now I've got the magnitude. That's just the magnitude. It's going to go in front of the cosine. Agreed, class? Then for the cosine thing, I have what? Cosine of n, omega naught is just 2 pi, right? Times t plus, then the phase angle associated with c of n, which is this phase angle, right? So it's the inverse tan of 2 pi, it's actually, I could put inverse tan, minus the inverse tan of pi over 10, n pi over 10. So it's going to be minus tan minus 1 of n pi over 10, and that would be in radians. And that's the phase angle associated with this, and that phase, wait a second. That is the phase angle associated with the transfer function. The phase angle associated with this Fourier series was what? It was you have your notes, it was plus what? What was the e to the j on the phase? E to the, yeah, that's gonna, yeah, that's n pi over 2, right? Is there a minus side front of that one?
Yes, I have a minus, yeah. Minus j pi.
Minus, and that's going to be n pi, that's it?
Yes.
Okay.
Minus j pi.
So, sorry?
Minus j pi over 2, right? N pi over 2, I think.
Pi over 2, sorry. Now, the thing about this is, that will give me the output in the time domain for that circuit. A lot of you are looking for, seems like a lot of work. Ultimately, the only thing you need is a transfer function and the values of c of n. And you can get the output. It really is that simple in this one. I wrote the whole thing down. When you actually do some MATLAB work on this stuff, you'll see it's, if you get about 5 or 6 terms, it gives you the exact output. Now, most of the time when we talk about EMC, that input has a rise time. But for me to put the rise time in there, it really takes some time on that board. Okay. Now, next, after this, 10 minutes. I know it seems like a lot, but this is actually EMC work. It's pertinent to a lot of stuff. Have y'all seen this anywhere else? No. Did you? Where'd you see? Not you. He's in my EMC class. He does. Did you see it anywhere? No. Anybody? I don't know if they do it in digital electronics or not. No? Okay. You had COM, right? Did you have anything like that, COM?
No, but I took common this summer, so the class was a little different.
Okay. Back to this thing. So now we're going to get into the actual frequency spectrum of this waveform. So when we have this waveform here with a rise time, fall time, this has rise time, tau rise, and on time of tau. Fall time equal to rise time, tau rise, at a given period, at a height A, period T, duty cycle equal duty time equal tau over T. So we come over there and we had those coefficients. I put that. Remember that I said that the C of n value for that was really A, and it was e to the minus j n, and this is going to be actually, let me do it this way. I want to show that I give you the form that I give you before. It was A over T, e to the minus j n omega naught, and here it's tau rise plus tau over 2. I'm going to leave it in terms of that. Then it's the sync function of n omega naught tau over 2 and it's the sync function of n omega tau rise over 2. That was the form, right? Here's where we go with this one. I'll let you just catch up. Now, what we really care about, remember what I said earlier, the envelope. We want the, I know this right here, the CNN that goes in the infinite series, all right, the exponential series. This is also the C of n that goes in the series I just showed you, where my V of t would be equal to C0 plus the summation from n equals 1 to infinity of 2 times magnitude of C of n here, and then it's going to be times the cosine of n omega naught t plus the phase angle of C of n. Now, hear me now. Each one of these terms is a phasor-like term, all right? Magnitude of phase at a constant frequency. When I take a look at this, and if I plot it, I'm going to change this a little bit. Plot the envelope right here, that magnitude. I'm going to show you something. This is important. So I'm going to take this, and I'm going to do a few things. First, I'm going to go ahead and let omega naught become 2 pi f naught. And f naught is just the fundamental frequency. It's 1 over the period. You with me on that? So I'll make sure I say this. 1 over t is equal to f naught. Now, after that, what I'm going to do is say that when I do this, and I'm going to do it over here. Now I'm going to say that n f naught in a second will become just the frequency. Right? Instead of having at discrete values of n f naught, now we're going to look at the actual behavior over all of f. All right, we're going to let n f naught become f. So over here, what this becomes is equal to a over t e to the minus jn omega naught over 2 here will become just pi times f naught tau plus tau rise. This will be of no consequence in a second. Then it's going to be times the sync function of n, and then where it becomes normally, it would be pi, n pi, and then it would be f naught, it would just be n pi, not n, pi, n f naught becomes f times tau, times the sync of pi f tau rise. Now this is important. Now, so when I take a look at this right here, and I put it in here, I see there's a 2 in front of it. You all with me? Now please, this is the bottom line. When I come over here, and I do this. This is an approximate estimate. It's not exact, but it gives a worst case, and that's really what I was looking for. Normally when we talk about EMC, in the real world, we look at the log of the frequency, and over here, we plot 20 times the log of the actual voltage waveform over 10 to the minus 6. Do y'all follow me? That would be dB microvolts. Does everybody know what dB microvolts are? This is a normal way it's done. When you actually plot this, for this waveform right here, there's a 2a in front of it. I mean, this become 2 because of this. And what you get is this, a value here, it'll be a DC value. Now, think about it, at low frequencies, right, these sync functions, the sync function is sine x over x. For small values of x, it's about 1. You all follow me? So when we're down in the frequency range around 0, it's really a couple of 1s right there. It's going to stay at a value, please write this value will be 20 times the log of the magnitude of 2 times the actual coefficient A times tau over t. Usually that duty cycle is going to be 1/2, so it's really just log of A. And then you divide that by 10 to the minus 6. So that will be this line. It'll continue, it'll be flat until the first break frequency, which is this one. When this right here becomes 1. So right here, the frequency where that becomes 1 is really pi f tau equal 1, or f is 1 over pi tau. Do y'all follow me on that? How many see this right here? If it seems a little much, just please hang on. This is the important part. So this first frequency that breaks that is going to be 1 over pi tau. And it's going to start going down at a rate at minus 20 dB per decade at that point. With me? Just hang on. 20 dB per decade, because now this thing looks like simply a 1 over f function. And 20 times the log of that is just going to be minus 20 times log of f. This one breaks when pi f tau rise equals 1, or really when f is equal to 1 over pi tau rise. But then it'll start falling an additional 20 dB per decade. So right here, this frequency is going to be 1 over pi tau rise. This is called a high frequency break. And from then on, it breaks at minus 40 dB per decade. Okay? And it keeps going. Now, if you wanted to know, if you wanted to know the value, and next time I'm going to beat up I'm going to do a bunch of example problems for you. I'm going to give you. You wanted to know the value of the actual output, you might say the voltage content at any given frequency. This is not power, but if you wanted to know the actual frequency voltage content, harmonic strength, at a given point there, we could get it or there. And I think I'm just about out of time, but I'm going to just show you this. And I know this is a lot. There's some example problems I'm going to give you, work through. But you need to keep up with this, because when you see them, you're going to realize they're not that bad. So, this is an approximate method. Hang on for 1 second. If I wanted to know the value, let's just say I want to know the value of this frequency right there. What I would do is say that value will be equal to the value here. So if I wanted to know the magnitude of this output, right to that, it would be 20 times the log right here of 2a times tau over t over 10 to the minus 6. Then, this first break frequency is at pi tau. So then it would be minus, now it's starting to go down to 20 dB per decade, 20 times the log here of the magnitude of the upper frequency. And I'll just say I wanted to know the voltage here at F, call it F1 right there. Upper frequency over the first break frequency, which is 1 over pi tau. That would be the value of that one. Do y'all follow me on that? You pick me a value of F, and that would give me, because remember, it's 20 dB per decade. If you don't go a decade, I mean, if this is 10 times this, 20 times the log of 1, or 20 times the log of 10 is 1, just be down 20 dB. But if you don't go a decade, then you have to adjust and say 20 times the log minus 20 times the log of the frequency you stopped at, divided by the frequency where the break was. Now, if you're beyond that, if you're over here, then what you have to do is first take the full decrease from here to here. So it would be 20 times the log of the second break frequency, which would be 1 over pi tau rise, and then you would have to take minus 40 times the log, because now you're breaking at 40 dB per decade, of whatever frequency you stop at over 1 over pi tau rise. I know I said a lot today, and you can do it. I'm going to give you some problems. I wanted to try to get this all done, so next time we do problems, we work a bunch of problems, and you see this worked out. But this is really MC. And this is why bandwidth and a lot of things like that don't really have a clear meaning. I mean, where's the bandwidth on that? A lot of times we have to know is the type of problem you're dealing with. This is really MC, and we'll talk about it. It's not just 1 over tau rise. I'll tell you that. That's what's in, or he says it's 1/2 over tau rise. That's hand waving in his book, Dr. Winston. He's trying to give you an estimate, but it's a very coarse estimate. Okay, I'm going to give you some problems, and now on Wednesday we're going to have a problem session on this stuff, and then we'll try to get this.